we go. Okay, YouTube. So, since today's topic is trees, how about we define what I'm talking about? You know, because I mean, when you think of trees, you think of this right now. When I think of trees, I think of this. Which in a way is actually the same thing as the right side, because if you take this quote unquote tree, you flip it upside down, that's pretty much it. It's the same thing at this point. Those are the branches, and these are your leaves, right? And that's kind of what makes a tree. So yeah, my mind has been blown, right? So yeah, there's no surprise as to why they call them trees. So let us go ahead and undo a couple of vocabulary definitions of what trees are. So first of all, so far you have been on the linear path of your life, right? You know, you're learning queues and linked lists and arrays and stacks, and even circular arrays are still just linear. It's just kind of a thing that goes in circle, but it's a line at the end of the day, right? And that's cool and all, but it's only a small subset of all of the different types of algorithms out there and ways of storing data structures. And so trees are not going to be a linear data structure. They're actually going to be what we call a hierarchical data structure. And I don't know if I pronounced that correctly, because it is kind of a fancy word, hierarchy. But I'll write it so that you all can figure out how to pronounce it later. Ask your English teachers. Hierarchical, I think is right. Okay? So trees are hierarchical data structures. Now, what does that mean, hierarchy? Hierarchy is like, it's harder to define it without actually showing a tree, because that's the best example. But when you think about like a computer, okay? A computer file structure system is hierarchical in nature, okay? So for example, if you're on Windows, you have your C drive, which is where all your information is stored if you have a single drive usually. And in that C drive, you may have different directories. In fact, let me take a look at my own C drive and see, although I do mess with computers and change things. But yeah, so you have a directory called program files. You have a directory called users, which contains all the user data usually. And you can have some custom directories that you throw in there. In my case, I have a folder that is like just my initials. And in that folder, I install coding stuff and blah, blah, blah. Okay? So let's just say that in this folder, I have a teaching folder, which I used to have that actually, but I moved things around. So made it more fancy. And I did read, by the way, something interesting about this, that so I'm a millennial by age, but the newer generations, I guess Gen Z or the one after, which I forgot the name of it, they already gave a name, they don't think about file structures in computers. They just store everything in a computer, like randomly, and then you use a search engine to find data, which is true when you think about a phone. Like a phone is really hard to actually manage a file structure. Like it's still kept in file structure, but like they obfuscate that because you don't need to know it. So unless you like download an app that lets you maneuver around the directories, you don't really think about that when you download or use files, right? I don't know. I don't know if that's the name of the generation, but yeah. But yeah, but yeah, it's viable because search time is a lot faster, so you don't really have to worry too much about storing things and searching when you can just search things quickly with indexing. But yeah, so I mean, maybe this example no longer resonates with younger people, although you guys are not that young anymore per se. I mean, you have to be at least 18 usually to be in college, unless you're like really, really smart. So yeah, you probably still use computers with file directories, but we'll see in 10 years what happens. Like when we get that new generation going up to the college. But yeah, so hopefully this example still resonates with you guys. But we have a directory in there, and maybe in here I'm teaching this semester like a ton of classes, like literally a ton of classes. So, I might be organized and keep directories for each class I'm teaching. So I have, 301, and then I have DA 621 that I'm teaching. And then, I might have subfolders in this one because I have 4 sections of this. 1, 2, 3, 4. Although section 4 has 0 students. So that's very cool. But yeah. So, this is the class schedule. But you, as a student, might have the same system except for the classes you're taking as a student, right? And you might have under here different folders for assignments, maybe for worksheets, and so on, right? So this structure is a hierarchy because, the root of all of this is the C folder. And then from there you have the subfolders, right? Which are contained there. And this allows you to organize information because it's very visually pleasing. Like you're like, okay, maybe this is not the best of names right there. But aside from that, that if you want to go to teaching or school or whatever, you call this school. In fact, I think, when I was in school, I had a folder that I called school instead of teaching. I just kind of changed the name to teaching once I stopped being a student. But yeah, so, folder of school and all my classes. And then you have in there also different assignments. And I don't know about you, but at least I was organized like that. Kind of OCD'd about it. But yeah, it made me easy to access to my files, right? Older generations sometimes will download a file like my dad, and he doesn't know where he downloaded to, and now he spends like 10 hours searching for it because he doesn't know how to use a search engine either. So he just literally hardcore goes into folders and searches, right? So the idea is you avoid that by keeping this organization, right? So essentially, this is a hierarchy. This is a way of storing data. You could also think of like a family tree, who your parents are, who your grandparents are, and how that branches out, basically. Although that is a little bit different in how you draw that tree, because, you might want to start with like a granddad. So, GD for granddad. But you usually need to have like a grandmom, because I guess you need 2 people. Well, actually, they could be, we want to be inclusive, so they don't have to be mom and dad, I guess. But the point is that, they want to be, genetically, you're getting 2 DNAs. So let's just say person 1 and person 2, okay? I don't want to get in trouble and stuff like that. But yeah, so, you put that together, and then like maybe you have 2 other people that got together to make a kid, and then they got together and made a kid, and that's you. But you could also have brothers, which kind of makes it harder to draw. So, but you get the idea, right? That they form trees, your family tree. And here's a catch. Today, we're mostly going to be talking about binary trees. But I want you to know, and that binary trees with the example actually with the families, because you need 2 sets of DNA to make a baby. But in things like the folders for my computer, they're not just binary, right? Like, here you have 4 different directories that are in here, right? So when you're making trees, you're not limited to a certain number of branches coming out of your tree. You could have like a million different directories. Like if you're super unorganized, you could have all your files and directories in your desktop, and like that would literally be like a tree with like a million branches, like blah 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 blah, everything from like one spot, and then that's still part of a tree, right? So ultimately, what I'm trying to get to here is that it's a completely different way of storing data than when you're used to when it comes to an array, okay? And it's going to be useful for things that, I'll explain to you all the usages, but I mean, hopefully just the basic usage of storing things in the computer can give you an obvious example as to why it's actually cool. Imagine storing all your data as an array. That would be the equivalent of like having a file cabinet, and you just dump papers in there without any sort of organization. Sure, you could sort it. Okay, fine. Dump it sorted. It's not bad, but it still sucks, like trying to find something. You gotta remember the name, and like then if you don't remember the name exactly, then like you're screwed, because like it's like when I go buy something, being from a foreign country, from Mexico, I have like 2-part last name, so like sometimes they understand that and they store like my first part of the last name under that, but sometimes they store them the second part of my last name. So like I tell them what my last name is, and they come back and like I went to pick up these glasses actually over the weekend, and I go and tell them like, okay, it's under this part of my name, and they look it up and they're like, nope, it's not there. I'm like, okay, try this one. Okay, it's on this one, right? So searching by just searching for something is not ideal if you don't know the exact name. Whereas hierarchy is useful because you're like, okay, I'm looking for something school related. Like I'm looking for something, I'm like, hey, I really like this assignment I gave in 302. Like, a couple of years ago, but I don't remember the assignment name or what number it was. Well, I know that if it was for 302, I can work my way here and then just like search on this subsection, right? So this can really speed up your access time. Okay? So, yeah. Yeah, no, I know. There's a lot of people that have issues with names. I guess I'm fortunate that that's the only issue with my name, but my name is relatively generic, simpler. But like people who have like symbols in their name, that makes it even harder for people to spelling. Although I do have an accent on my middle name, like Ramon has an accent, but like I just say like, yeah, just forget about the accent. So like, it doesn't want to break the system, you know, crash their servers because I'm using a non-ASCII character. But yeah, okay. So all right, that's a little introduction. So let's define some terms that I kind of been already mentioning. Okay, so when you have a basic tree, you know, the tree is going to be the complete structure, and your tree is going to be made up of the components, right? And the components are going to be located at the end, at the here, or up here, right? These components have a lot of names, but I prefer the component name of node. So the nodes of the tree, that's a good term to use. There is a special name for the nodes that are at the bottom of the tree. So those nodes at the bottom of the tree, I called them already by that name earlier. I said leaves. And think about like an actual tree. The leaves are at the end of the branch, right? So leaves are going to be the nodes at the bottom. And there's a better definition for this. I'll give it to you in a second. And then finally, all the way at the top of the tree, which you can think of like what's coming from the ground, that's going to be called the root of the tree again. No surprise there. These people were thinking of trees when they named this. So, yeah. Okay, so let's go ahead and define properly what a leaf is, okay? So a leaf node is a node with no children. Now, for us to understand that, we need to understand what I mean by children, okay? So when you're looking at a node, this node is just solo. It's like solo in life. It's a single node, has no children. This could be considered a root actually, but that's not the point. The point is that it's not considered, it technically is considered at this point a leaf. It has no children, okay? But let's say it has one children. The way you know the children is, you don't have to put arrows. Sometimes you'll see them with arrows, but you put it at the bottom. Okay, we typically, you know, we kind of decide to draw trees in this direction, from root to leaf, from top to bottom, okay? Don't go hardcore on the TA and like flip it upside down on the task. The TA will get confused and give you a bad grade. So let's just agree to that consensus for now, okay? So this node is no longer is not considered to be a parent because it has a kid, and this is considered to be the child. Okay, so if we have two nodes like this, we have a parent node and we have a child node. Okay, if this node decides to have a kid or two kids even, then technically speaking, this node is a child of the parent node. So this is a child of this, but it's also considered the parent of the new two kids. Okay, so it's also a parent at the same time. So, you know, everybody in the world is somebody's child, right? Unless you're like Anakin and just were born out of nothing, right? Otherwise, you have parents, or you had at some point. You know, sad moment, I guess. But the point is, you were made by someone. So you know, everybody's somebody's child. And if you have kids, then you would also be a parent, right? So that's kind of the idea here, okay? But I'm still gonna unmark those just to not confuse you if you're like looking at this in the future and reviewing. I just want to make sure you understand that that's a parent and there's a child, okay? So a leaf node is considered any node that is like a single. It has no kids. So it's always going to be at the bottom, right? So if you have a tree like this, then the leaf nodes are always going to be at the bottom, but bottom of its sort of section, because you see this has no kids, no kids, no kids, no kids, no kids, and no kids. However, everything else is not a leaf node, because this has a kid, one kid. This has two kids, one, two, 1. Okay? So all the red ones are going to be not leaf nodes, and all the gray ones are going to be considered leaf nodes. Okay? And yeah, that's probably why I like it too, because node does remind me of linked list as well. Or maybe I think of linked list node because of tree nodes. I don't know which one I learned first. So the grandparent term is useful to know, sure. Like if you have something like this, yes, you can call this a grandparent, but it's not very often that you hear the term grandparent, because technically speaking, a grandparent's also a parent, So yes, if somebody says to you like, "Hey, look at the grandparent," now I think you will understand that it means like two generations up per se, but it's not very like popular. Like you won't see the word grandparent mentioned in like an algorithm. But I will sometimes talk about nodes as the grandparent node, especially when we're doing a rotation in an ABL tree. Then actually grandparent becomes a useful term. Okay. So yes, good point for bringing that up. So leaf nodes are going to be nodes with no children, and the root node does not have a parent. Okay, so the root node does not have a parent. It's that Anakin Skywalker. Okay. Topmost node. The elements that are directly under an element called children. That's kind of what it said. Okay, those are all the terms that I wanted to cover, I think. Root, leaf, node, child, parent, and leaf. Yeah, okay. Good. So those are the basic terms, all right? Moving on to some more interesting things are, when you just say tree, as I'm doing right now, I'm not specifying any sort of degree or anything of the tree. The word degree is a term that we're going to talk about when we get to graphs, but it means that when you have the concept of vertices and edges in graphs, right? So the vertex is the actual node of a graph, and the lines connecting your graph, those are going to be your edges, right? And so again, you can call them, instead of vertices, you can call them nodes in graphs. But the point is that when you're looking at how many edges are coming out of a node, that's called the out degree. And how many edges are coming into the node, if it's directed, that's just called the in degree. If it's undirected, such as here where there's no arrows, you just call it the degree. So what that would mean would be that this is a degree of 2, whereas this is a degree of 2, whereas these are degrees of 1s, okay? So just a little teaser, but we're not to graphs yet, so don't worry too much about that yet. The point is that when you have a tree and you put a limitation on the number of children it could have, which is code for that degree thing I'm talking about, you decide what type of tree it is. So if you think about a binary tree, which is the subcategory of trees that we're going to be looking at for a few weeks before we move on to graphs, a binary tree is going to be a tree with one special row. They use the word elements in Geeks for You, so I'm going to put that word as well there. But yeah, so a binary tree is going to be a tree whose nodes can have at most two children. So like, think about like when China had the one child law, basically. It would be not a binary tree, I guess, but there would be a unary tree. Because unary, as the name implies, means one child at most, okay? So this is like not as strict as China, but, well, China changed that law, by the way. But, before that, imagine that we had a 2 children limit, okay? That would be what a binary tree is, okay? So it can have at most 2 children. So let me give you examples of what binary trees might look like. The most easy example to understand is this. We have a node and it has 2 children. That's a binary tree. This is also a binary tree. Even though, this node only has one kid, it's still a binary tree because it can have at most 2. It doesn't mean you have to have it. It just means you can, but you can't have more. If you're limited to having 1 kid, you can also have no kids at all. It's not like you have to have the kid. It's optional. By that same token, that can be considered a binary tree, even though it's just a single node. This can also be considered a binary tree because, again, it's only one kid, one at a time, but, it's still under. Let me give you examples of what is not a binary tree. That's not a binary tree. Reason being, everything was okay except until that kid here. They had 3, so that violates it. This would actually be a ternary tree. Spell that. Okay? But again, not what we care about. Do they? I know they removed the single kid law, but I don't know if they actually implemented another one. So I thought it was just like freedom now to have any kids, but who knows? But if they do, then that's cool. So I guess they have ternary tree law. Yeah. So if we were talking about only unary trees, then it would have to be like this, by the way. Hopefully you kind of understand the logic that these are subsets. So all unary trees are subsets of binary trees, which means that any unary tree can be considered a binary tree. It's just a special case, I guess, technically. It just means, like, if you say ternary tree, that means that you can have up to 10 leaves, 10 branches, 10 like childs. But, if you have no childs, then that's still technically any degree of tree. So, yeah. Oh, that's cool. That's good because we have the population crisis issues. So we have too much old people and too few young people to support the old people. So like bad things are happening to the economies and whatnot in the future. So off-topic discussion, but yes, very, very dangerous situation in the world with population right now. So yeah, okay. So why do we care a lot about binary trees? Well, because there's a really cool usage for them. First of all, think about it. Computers are in binary, right? Zeros and ones. So like, that already gives you a hint that we like things to being in binary because they're easy to implement in a computer and to deal with a computer. But also we can use the trees for things like decisions, right? So if you have a binary tree, it means that we can have a left child and a right child, right? So if I draw a tree, this is my parent / root, and this is considered to be, well, here, don't put the R on the side, so you're gonna confuse. This is the left child, and this is the right child. Right child sounds like this one's better, but you hear what I mean, right? And so ultimately, if you can make this be a decision tree. Now here's something that is definitely not something I would expect you to know, but I'll still mention it for those of you here that are a little bit more closer to my age. When I was a kid, I wasn't really into this, but I was aware it existed. That there was this thing called paper, and back when we had paper, there was magazines, and you could buy them at stores, and before the technology world. And so in these magazines, these mystical magazines, at least I guess they were more targeted at like teenage girls. They would have quizzes like, does he like me or not, or like actually no, sometimes I saw it once for like deciding what career you want to do. Like, do you want to be do you want to be an engineer? Do you want to be like a lawyer or a doctor? And so the way those quizzes would work is they would ask you, yes, I think dialogue tree is actually the name. They would ask you like, okay, do you like math? And then if you answer yes, so like the question would be, do you like math? And if you answer yes, you would go to this question. And if you answer no, you would go to that question. And then this would be like, okay, do you like computers? You know. And if you answer yes, you go to here, and it would be like, okay, go do computer science. If you answer no, then it would be like, go do mechanical engineering. And if you answer no here, it said like, okay, well, do you like to take care of someone? It'd be like, okay, go be doctor, or if you don't, then go be a lawyer, or whatever, you know. So yeah, so ultimately these things were pretty good example of that. But again, I don't expect you guys to ever done those. I barely got to see that before I moved on into the technological world. But yeah, so those were a thing back then. So ultimately, these are known as decision trees. And they can be very useful for actually for accessing data, not just for deciding what career you want to be. So for example, let's say that you're trying to store a couple of numbers, okay, in this tree, and you want to make it, you know, fast access. Because right now we are currently at well, if we include the sorting time, it's n log n, right? Because it takes n log n time to sort, and then once you sort it, then you can do binary search on that, which takes log n time. So, you know, this is a one-time expense, and after that, it takes log n time to access things, right? It's not particularly bad. The problem comes in when you try to actually insert new things. Inserting new things into an array is going to potentially take, well, it's going to take log n time to figure out maybe where to insert it. And then from there, you have to shift things around, which is going to take n time potentially. So, you know, it's not ideal, but it's not bad, but it's not ideal, okay? With this, it's going to be a little bit faster than that. We're going to actually stay in the log n world, with an exception of building it as well. But ultimately, let's just put in some numbers so you can see what I'm talking about. So let's just say that we have this little tree with numbers in it, okay? Don't worry too much about how I'm making this for now. Now let's just leave it like that, okay? So suppose that I have this tree right here. And I would like to ask you, you have this, well, you don't know it's a tree. You just know that it's some data. And I could ask you the question, hey, is number 8 in my data? Well, you can do it like a quiz. You can look at the 5 and say, okay, the number I'm looking at, is it bigger than 5 or is it smaller than 5? Well, 8 is bigger than 5. So let's try checking here. Then you see the 10. You're like, okay, well, is the number you're looking for bigger than 10 or smaller than 10? Well, it's smaller than 10. So then go to the left side. Is the number you're looking for bigger than 8 or smaller than 8? You're like, well, actually 8 is what I'm looking for. Oh, well, there you go. You have it. How many checks was that? 1, 2, 3 checks. 1, 2, 3. That's pretty good. Obviously, if you look for 5, you would have found it immediately. But the point is that in the worst case scenario here, you're only going to be doing 3 checks. Because let's say you're looking for the number 3. Okay? If you're looking for the number 3, you start with the 5 and you say, okay, is the number 5 in my list? Or sorry, number 3 in my list? Well, it's smaller than 5. Okay, so check here. Is the number 3 here? Well, it's smaller than 4. So go to the left. You get to the 2 and you're like, well, is the number here? Well, 3 is bigger than 2, so it should be to the right. But guess what? There's no children here. So because there's no children, as long as this organization that I'm doing is follow through, where I'm keeping numbers less than on the left side and numbers greater than on the right side, then I can go back and say, hey, 3 is not in my list. And again, it only took 3 checks. This is what is known as a binary search tree. And it's very useful for storing data and accessing it quickly. Okay? So big usage of binary trees. Facebook quizzes. Did they have those? Yeah, that's probably like the evolution of like magazines to that. So yeah. I don't know the connection you're making to Quicksort on this. That one I'm not totally sure how you're making that connection. But if that makes sense to you, then who am I to question that? So yeah. So there's a link with like a very trivial implementation of a tree from Geeks for Geeks. I'll post that on the description at some point for those on YouTube. And then for you guys, let me just search it. Binary trees, Geeks for Geeks. There's really good stuff for binary trees on Geeks for Geeks. Definitely a good place to study and review things later on. But I'll talk about the actual code implementation of a tree maybe next time. Maybe this time, but maybe next time, okay? It's very trivial, actually. It's a lot like a linked list, but you just have 2 pointers, like somebody said earlier, okay? So that's a binary tree, and this is a binary search tree. And again, the big power of this is be able to decide whether things are yes or no, or in this case, whether it's bigger or less than. And if it's equal, then you just keep it there, right? Okay, but this is stepping a little bit ahead, just kind of showing you what we're going to get to. Again, this is the fun stuff, but we're not there yet. First, let's talk about the properties that I'm dreading to talk about, okay? In fact, I might save some time if I haven't written already from the last time around. So let me try to copy them here from the last semester. See if I have them. I presume I do, because I usually write them out. I do. Okay, this is great. So we can actually save a little bit of time. And these are also going to come from Geeks for Geeks as well, so you can see them there too. Okay, so these are known as binary tree properties. How can binary trees sort nodes by letters? You'll see that when we do the letters. You know, you can basically say whether a letter is greater than or less than another letter. So, yeah. Ignore the door doing weird things. So, yeah. Okay. So, let's just talk about these one at a time and understand them. Okay. And the reason why we want to talk about these properties is because, like, when people develop all these algorithms for trees, they didn't just magically come up with them. They did them based upon these properties and how they work, and you know, understanding trees so that you can use them, right? You want to understand your tools so that you can use them effectively. And so that's kind of what this is about with the properties. So yeah, let's start out by defining what this word level means before we can actually explain what this property is. So since you were talking about letters, let's just go ahead and draw a tree with some letters in it, okay? This time I'm not going to do that property about whether the letter is bigger or less than. I'm just going to draw a tree with letters, okay? Let's just say this is a computer directory of some stuff. Okay? So when I have something like this, when I say the word level, what I'm talking about is the different, as obvious as it sounds, the different levels of this tree. So you can think about the distance that those nodes are from the root. So when you have the root, you can consider this to be kind of like the base level, okay? Level 0, level 1, depending on how you're going to do the math, which I'll come back to what I'm saying with that. From there, the next sort of level is going to be all the nodes that are one jump or one generation, one kid from the root. So that would be this. From there, we have all the nodes that are a distance of 2 from the root. So usually the levels are going to look pretty even like this, unless of course you don't draw your trees pretty, which I'm guilty of that as much as anybody else. So I have an example of that here from last year. So like, let's say you write a tree like this. Okay, technically speaking, in this nasty tree, this is one level, and then the next level is this node and actually this node, right? It's just because the tree is kind of drawn poorly that it looks like that. So this might be misleading because you might be misled to say, well, all these three are one level, but they're not, because technically the T is only one generation away from the A. It's the kid. It's actually the brother of B. So we don't use really the terms brother or sisters for it though. But yeah, you know what I'm saying. So that's the only thing you got to be careful about when you're working with levels, that you don't screw up figuring out whether something is on the same level as something else because you draw the tree wrong. So yeah, T is actually the uncles. Yeah, it's the Uncle T. Uncle T. I feel like that I've heard that somewhere. What is that? I don't know. Okay, yeah, whatever. Okay. So anyways, that's what level means, okay? So going back, now that we know what this word level means, this might make a little more sense. So the property says the maximum number of nodes at a certain level, L, of a binary tree is 2 to the L. Oh yeah, that's probably what I'm thinking of, Mr. T from the show, the A-Team. So yeah. So basically, what this is saying is if you want to count how many nodes there are at a particular level, it's a very easy thing to do. Just go 2 to the power of whatever the level you're at. Caveat with that is, again, if you have to consider for this to work, the root level to be level 0. Otherwise, it doesn't work. What I'm saying by that is, if we're looking at this tree right here, level 0 would be 2 to the 0, 2 to the 1, 2 to the second, and so on, right? So what is 2 to the 1 is 2, 2 to the 4 is 4, and then don't forget that we talk about exponents. What any number to the power of 0 is equal to is 1, okay? So with that said, it should be obvious that at level 0, the most nodes you can have is A. So again, I guess, yeah. Well, you say that, but there's MATLAB that starts from 1, and there's like, I forgot if it's Fortran or Pascal that starts from 1 too. And then like War 3 starts because we just claim arrays start from 0. So we have to be careful about that stuff, But yeah, so I guess in this scenario, it makes sense to us that this should be level 0, okay? But you just wait until you get to height and all these terms here. It's going to get messy. So what I'm saying is that these levels, the maximum amount of nodes they can have are these. So that makes sense for this one, and the last one, you're like, well, there's only 3 nodes there. Yes, right now, because we're saying the maximum. Why? Because every parent can have 2 childs, right? And in this case, C only has Mr. T. But if he has Mr. G, how about E for Mr. E? Like the dude from Batman, right? Then you can see there's 4. And if we do the next level after that, let's just do some little bit more space here. You can see that each one has 2, right? So here I'm just going to use numbers now. Too much effort otherwise. So this is 2 to the 3rd, which is 8, which actually makes sense because there's 8. So think math world for a second here as to why this is kind of obvious. Like, these things are multiplying and doubling every time. So you can see how it goes from 8 to 16, and then 16 to 32, 32 to 64, and so on, right? That's why this property works. It's an obvious property once you see that, but it's easy to forget that this is a thing. And we're strictly talking about the number of nodes at the level. We're not talking about the entire tree. Okay? We'll see that in another of the properties. Oh, actually, that's the next property. So that's levels. So it's when you're coding a tree, there's different ways of allocating memory for the tree. You could actually code a tree in an array. As weird as that sounds, you can. You don't have to use pointers like linked list. Although it's preferred to use pointers for a lot of the different types of trees you make. So, when you're allocating memory, if you need to allocate memory for a level, and you need to find out quickly like how much memory you need, you can just go 2 to the power of that level. And then, that's your dynamic allocation right there. So, can come in useful there, okay? Okay, property number 2. The maximum number of nodes in a binary tree of height h is 2 to the h minus 1. So here we have this term height, okay? So the term height, when it comes to a tree, is going to basically be the generation, okay? So it's kinda like the level term, but this is where like things get messy with how they're defining things, okay? So first of all, let's compute what the height would be if it's equal to 0, to 1, to 2, and to 3, okay? Because I want you to see something that's kind of annoying here. So in this case, it's 2 to the 0 minus 1, 2 to the 1 minus 1, 2 to the 2 minus 1, 2 to the 3 minus 1. This is equal to 0. 1 minus 1 is 0. This is equal to 1. 2 minus 1 is 1. Then here it's 4 minus 1, which is 3. 8 minus 1, which is 7. Okay? So this is so before we were looking at the number of nodes at a certain level. Now we're wanting to see the number of nodes of the entire tree. This is definitely useful when you're allocating memory if you want to make sure that you have enough space for a certain height of a tree. This is where your array start from 0 thing kind of gets wonky, okay? We can consider this to be level 0, right? The root level to be level 0. But here, nothingness is height 0, okay? So we're saying that if we have a tree of height 0, that's an empty tree, okay? So an H0 tree means that it can have no nodes. So it's just an empty tree. And then a tree with a single node is a tree of height 1. And then a tree with height 2 is actually going to be a tree with 2 levels. Okay? And then finally H3 would be something like this. So this is where like it gets trippy when you start counting from 0 and whatnot, because like, if I ask you like the number of levels this has, you start counting from 0, you say, well, this has 2 levels, right? 0, 1, and 2, right? And that's kind of what we were doing here. So you could say like, this is 2 levels, but it's technically height 3. It's like, it gets kind of wonky. And also you can consider like height to be the number of edges. So you see 2 of them. So you like, why is it 3? So it's not just something that I'm complaining about. This is an issue that is like in general, because depending on the source that you go to, Geeks for Geeks or someone's book or Stack Overflow or whatever, different people have different definitions for what height is. Some people are like, screw this. I don't want to say that this is height 0. I'm going to say that like height 0 is a single node, and then like there's no value for an empty list. There's like, that doesn't have a definition for height. And so then this matches more the levels definition. So it goes 0, 1, and 2 instead of just going basically, like 0, 1, 2, 3. Okay? So when I ask you in a test, like what the height of a tree is, I will accept either answer, but you have to define what you consider to be height 0, so that I can understand that we're on the same page. Okay? So yeah, I'm warning you, when you go online and resources and try to like get more material, it gets wonky with that. All you gotta do to fix this stuff is subtract 1 from it, essentially, to fix this. But okay, just if we're going with the one that I'm looking at, height 0 is considered the empty tree, and then height 1 is a single node. Okay. Why is height a useful concept instead of using levels? Because most people don't really talk about levels as a term, but you'll see height be used a lot, because height tells me more about a tree. Like, what the height of a tree is tells me like how far something goes. Because here's the thing, if I ask you what the height of a tree is, and you have a tree like this, so this is a tree you have. When you're trying to figure out what the height of a tree is, you're going to look at the biggest. Because like, think about a tree, like a real tree in the world, like green and whatnot. If I ask you how tall a tree is, or how high a tree is, you're going to go and measure from the bottom of the tree to the highest point of the tree, right? You're not going to measure to like the side of the tree. You're going to measure to the top, right? So if we go ahead and flip this into tree mode, into real tree mode, when you're measuring how tall this tree is compared to you, so this is you right here, what you do is you take your tape measure and you're going to measure to the top of the tree. So probably there. from the tree, right? From the bottom to the top. So very similarly, when we're trying to analyze trees as a data structure, the height of a tree is going to be measured as the longest node from the root, meaning that these two nodes are the farthest away that you can get from the root. And so we will measure the height of the tree as a basis of that, which some people might say, oh, well, this is, 1, 2, 3, so this is height 3. But that's making a different assumption, because if you go with the one that I told you, then this is height 0. Nothing is height 0. This is height 1, height 2, height 3, height 4, right? So this would actually be height 4 based on this definition of height. But technically speaking, height 3 is a valid answer as well, as long as you consider a single node to be height 0 and not height 1, okay? So in general, height is useful, level not so useful. So yeah. Okay, so again, these are just terminologies that you have to be aware of. So when you run into them in an algorithm that says, well, to compute the next step in the algorithm, compute the height of blah, 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 then you're like, okay, I know what they're talking about when they say height, or compute the level of this and that. Well, level is strictly talking about what level you're looking at. You don't really say, like, what's the level of a tree? That's not really a thing you ask. You ask what the height of a tree is. And then you want to go to a specific spot in the tree, you say go to this level. So level is like locating specific spot in the tree. Height is just talking about how big the tree is. Okay? So if I say, draw me a tree of height 5, then you know how, at least, how big it has to have that many, that many different levels per se. But then if I say, okay, draw me a tree of height 5 and then add this node to the second level, that's how you would communicate to somebody to add something to a specific spot. Okay? And the height and the level may be equal or not, depending on, again, what your definition of height is. In my definition here of height, they're not equal. Height is always plus 1 of the level. But if you can make them equal, you just have to change what the definition of height 0 is from nothingness to that. So basically shift these down by 1. So, yeah. To find the max number, we have to consider the root node 1, or else it won't work. What I mean is that if you're using this version of height where like nothing is height 0, then this formula will work by just plugging in 2 to the power of h minus 1. But if you're considering that the single node is height actually 0 and not height 1, then to compensate for your formula, it's going to be off. It's going to be off by a level. So you have to subtract that from that. So that's what I'm talking about. That if you're trying to compute, what the number of nodes of a tree is, because if I say, okay, I would like to know how many nodes I can fit in a tree of height 3. Well, that's 2 to the third minus 1, so that's 2 to the power of 3, which is 8 minus 1 is 7. So I can put in a tree 7 nodes, okay? So what that would look like would be one, 2, 3, 4, 5, 6, 7, like that, okay? So there you have a tree of height 3. Here's one way that you can kind of help you out to better understand this. Instead of counting the number of edges, count the number of nodes that you see. Because you can see here that you see 3 nodes, right? So you see 3 nodes, and this happens to be height of 3. If you see a single node, then that's height of 1 because you see 1 node. So you can also use the node number instead of the lines to count. Okay? So yeah, whatever works for you. Just warning you. The consensus here is not very clean amongst the scientific community per se, on what the height should be or something. So yeah, just be aware of that, okay? Write a note somewhere so that when you're taking a test, you actually use the same definition as me, or at least you specify that you're using the other definition. So if I say draw a tree of height 5 and have the second level have 3 nodes in it, you know what I'm talking about. you know, versus like, oh shoot, what does that mean? Which is what's level 3, what's level 5, what's height 5, like what is happening here? That's what I'm saying. We want to make sure we're on the same page with these terminologies. Okay, moving on. I think it gets worse, but does it get worse? Nah, actually that's as worse as it gets with terminology. So this one, in a binary tree with n nodes, n being a number of nodes, the minimum possible height or minimum number of levels, so here we're mixing matching, is going to be log n plus 1, and then you see the little brackets at the top. Anybody know what those mean when you see that? I'll kind of write them nicer so you can see them better. Roundup. Yeah, that's pretty much what it means. The official fancy name is known as ceiling function. But yes, that's literally what it means, that you round up. So whatever number you're going to get with this log, you know, logs, I know when we did the recurrence relations, we mostly stuck to like easy numbers that round, like, you know, log 2 of 8, you know, nice, it's just 3. But then somebody throws at you says log 2 of 9, you're like, oh snap, this is no longer easy because it's like decimals involved, right? Well, here we're still making it easy because you just round up those decimals. Problem solved. That means that if you have the ceiling function as a value 2.1 and the value 2.9, they're both going to round up to 3. So even 2.1 is going to round up to 3. So 2.0001 will round up to 3, okay? So that's what ceiling function means, or round up function, whatever you want to call it. So what this property is saying is that if you're trying to figure out, okay, you know, like one of the things you might need, you know, when you build a tree, you can build a tree of height 10 and have a great range of nodes, anywhere from like, you know, like 10 nodes pretty much to having like 2 to the power of basically 9 or 10 actually, and that's just the last level. So you could have a ton of nodes, okay, like a ton of nodes. So what this is saying is, what if you want to make the smallest tree possible for the data that you have, like the most compressed tree? And there's reasons for this. Like maybe just to tease you on those reasons, think about like the number search that we did here. Where's that at? Here, you know, the smaller the height, the less questions you got to get before you get to the end of your quiz. The less questions you got to do, the less work. The less work you got to do, the faster you finish. As we know, that's a win, time complexity wise, right? So if you're trying to make the most compressed tree, the tiniest tree possible, that's still a binary tree, meaning you can only have up to 2 children per node, then you kind of want to squeeze it, right? So if you want to find out, okay, cool, assuming I do squeeze it as much as I can, what's the minimum height that I gotta do? Because that'll tell me how much memory you allocate and things like that. Well, you just plug it into this formula and you're good to go. So if we have 100 nodes, you know, that we gotta insert, we put in n equals 100, and 100 plus 1 is 101, and we take the log of that. That's gonna be, I don't know, 7.2. Let's see, 6.6. Ooh, I was off. 6.658211. Blah blah blah. Okay. The point is that 6 point. You round that up to 7. So, you know, that goes up. That's not I don't know if that's a real symbol with the equal and the up, but that's what I'm going to do. You round it up to 7. Okay? What this means is that the minimum height of a binary tree that I have to do to fit 100 nodes, and by the way, it doesn't mean that the last level is going to be full or that the tree is going to be full, but I'm saying, you know, there'll still be a couple of different combinations you can make, but you will not be able to make it with less than 7 of height. Again, this is using the definition of the height that I said earlier, So, things might get iffy otherwise. You might have to +1 or -1 every one of these examples if you're using the other definition of that. Shall we prove it? That's a lot of nodes to draw. So let's do a smaller number. Let's prove a number like 20. Okay, that's a little bit easier. I'm not drawing for 10 days here, but you feel free to try it at home. Try it at home to draw, not right now, but like later, maybe after the test when you're just relaxed. Try to make the tree and try to fit them all into 7 levels or height of 7. Okay. But for me, I'm just going to do 20 here. 20 is going to be the log of 21. So let's see what that is equal to. Like, I want to see the actual exact number. 4.39. So that becomes 5. So that's saying that we need 5 for that. So let us see. So what do we got so far? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we got 15 so far and we need 20. So hopefully you see by now that this will work. 16, 17, 18, 19, and then 20. Okay? So there you go. You got a really nice and compressed tree. How many levels do we have? 1, 2, 3, 4, 5. 5. Or height of 5, which is what we got. Okay? So I don't know why I counted in Spanish there, but yeah. That was random. Okay, but yeah, so here's the point though. You can see we have space here in this last level. So it doesn't have to mean that it is maxed out, but it just means that we just had to have this extra level here. That also means that like this is a legit tree. This is legit. So I can play around and move these nodes like, I can move this one here. I can move this one here, and so on, right? So I can move them around there. So there's no one unique solution. There might be if the level was full, there might be, but yeah, all this is saying is, how many levels you need, which again is good for optimization of your code. Okay, so that's property 3. 2 more, to go, but we are out of time, so I will stop there. Like I said, these aren't the most exciting of properties, but trust me, when we get to them, things will get fun. Okay, so yeah, that is the end of the. Because I mean, I could go and do another property, but it's gonna take me like 20 minutes. We have 1 minute left of class, so yeah, hopefully this kind of gets you going. Got the terms: tree, node, child, parent, leaf, height, level, ceiling function, root, binary, unary, ternary, and that's it, right? Those are all the terms that you're gonna learn. So yeah, but yeah. So, and remember, the height and the level thing can be off by 1 based on your definition of it. So you always specify that to someone, and always make sure you're on the same page as an algorithm that you're reading. Because if you're reading an algorithm and they're using a different definition of height, it's gonna break things and be painful. So yeah, just be aware of that. So that is all I have for you today. So with that, I wish you all the best of luck with the exam. Don't freak out too much about it. Definitely, take it seriously, but don't make it the end of the world if you don't do good on it. Because I mean, at the end of the day, it's just a test. So, but as long as you know your stuff, you should be okay. It's open notes, so that's not, you don't have to memorize things. You have to know how to do them quickly. So definitely make a cheat sheet and it's gonna be fine. So yes, what does fine stand for? I forgot, but it's like a meme, right? I forgot, but There's a movie where they made a joke about that, but whatever. Ah, it's actually maybe this is pretty toxic. Fine, feeling insecure, neurotic, and emotional. I don't know if that's what the movie used. That's pretty toxic, actually. Didn't think about that. Okay, but yeah, no. Seriously though, just don't think about it too much. Just do your best and move on with your life, kind of thing. Okay. So yeah, I mean, you're getting extra credit for being here, so that'll help you out if you all do bad in the test. And there's a curve, so if you all do bad in the test, then you're all okay, kind of. So still do your best, and that's it. All right. Cool. So you all know where to reach me for the last minute stuff, if anything comes up. But yeah, that's pretty much it. And yeah, I do think, in my opinion, that the recurrence relations is the hardest because that's what historically I have seen students do the worst in. So most people get like the first questions right with the n squared being greater than n cubed and whatnot. Sometimes they'll screw up one or two numbers and lose some points. So you gotta definitely, I would recommend you to double check that question. Yeah, definitely double check your answer on that. Like, look at it one more time when you finish and make sure that you actually did not flip some things. Because like a lot of people make these obvious mistakes that I've seen in the past. That's like the easy mistake you can not make. But yes, historically, people have bombed the most the recurrence relation question. Like, yes. Like, I literally spent so much more time last time around or the semester before with recurrence relations just as an experiment to see if people will do better. Same story. So yeah, if you'd like to see any sort of like solution for the worksheet, just contact the TA. But I think worksheet 3 is unrelated to the test, right? Because we only have 2 worksheets. Yeah. But yeah, just talk to the TA and he'll go over it with you. And he does have office hours right before the test, I think. So I wouldn't wait until that last moment, but definitely could be a good spot for last minute questions. Okay. And I'm around, so just post on Discord and stuff. All right. Cool. Well, you're not the only ones taking the test. Take solace in the fact that the 202 students are taking a test too, and that for them that feels like the hardest thing they'll ever have in their life, probably. Little do they know about 302, right? And little do you know about 460. But don't worry, you'll reminisce and be like, oh, I remember the good old days when easy stuff was coming in 302, and now I gotta figure out how to do this LR1 parse table and follow sets and all that stuff. So yeah, this will be a piece of cake by then. So think about the big picture. You'll be laughing about this stuff, even for the later test. So yeah, except recurrence relations, that always stays hard forever, but that's okay. All right, then, that's it. I am going to take a 5-minute break between my next class. So I'll catch you all later. No class on Wednesday. Don't show up. There will be no stream. And yeah, see you next Monday. Bye, everyone. Good luck.